What NASA found on Jupiter, the planet of storms. From the moment Galileo Galilei lifted his small telescope to the night sky in 1610 and saw four bright points moving around Jupiter, humankind understood that not everything revolved around Earth. Those moons, Io, Europa, Ganymede, and Callisto, marked the first discovery of celestial bodies orbiting another world, and they became the cornerstone of a new cosmic order. Jupiter was not merely a planet, it was a system, a miniature solar system bound by gravity and light. For centuries, that vision remained abstract, its bands and storms glimpsed only as shifting hues through small telescopes. But in the 20th century, technology gave us wings, and the planet that had been a dot of color in the piece became an entire realm to explore. Jupiter was the first of the outer planets to be visited by spacecraft. In 1973, Pioneer 10 became humanity's first emissary to cross the asteroid belt and gaze upon the gas giant close-up. It was an act of courage as much as engineering. No one knew whether the high radiation environment would destroy the probe. But Pioneer 10 survived, swooping within 132,000 kilometers of Jupiter's clouds. Its instruments measured the planet's magnetic field, radiation belts, and mass with unprecedented accuracy. For the first time, the blurry orb of Jupiter resolved into a world of intricate belts and zones, swirling layers of ammonia, hydrogen, and water clouds stretched by fierce winds that circled the planet in alternating east-west bands. A year later, Pioneer 11 followed, photographing the Great Red Spot at close range and mapping the planet's polar regions. The data they returned were primitive by modern standards, but revolutionary for their time. Jupiter was revealed as a churning ocean of gas, with temperatures plunging below 100 degrees Celsius in its upper atmosphere and pressures rising toward incomprehensible depths. If the pioneers were scouts, the next missions were storytellers. In 1979, Voyager 1 and Voyager 2 performed their twin flybys, turning Jupiter from an astronomical object into a living world of motion. Their cameras captured more than 33,000 images in color and detail that no one had imagined possible. They revealed cloud systems braided into turbulent ribbons, ovals within ovals, and lightning flashes illuminating the night side. The Great Red Spot, once thought eternal, was seen to evolve, a storm larger than Earth, swirling at hundreds of kilometers per hour, yet subtly changing shape. Voyager's instruments measured temperatures, radio waves, and magnetic fields that dwarfed any other planetary environment. Yet Jupiter itself was only half the revelation. Its moons stunned the world. As Voyager 1 approached Io, the innermost of the Galilean moons, it recorded a landscape of sulfur plains and volcanic peaks. Just days later, Voyager's cameras captured an eruption in progress, a jet of gas and dust towering 300 kilometers high. Io was the first active volcano world ever discovered beyond Earth, its interior heated not by sunlight but by tidal forces, the gravitational tug of Jupiter stretching and squeezing it like a ball of molten wax. Further out, Europa appeared smooth and bright, crisscrossed by a network of dark lines. Its surface resembled cracked sea ice, hinting at an ocean hidden beneath. Beyond it, Ganymede revealed vast, grooved terrains, evidence of internal activity, and Callisto, the outermost, lay pockmarked and ancient, a record of the solar system's bombardment. The Jupiter system, once imagined as a static collection of moons, became an ecosystem, each moon a world in itself, shaped by the power of the planet they orbited. Voyager's discoveries transformed planetary science overnight and set the stage for decades of exploration. After the Voyagers continued towards Saturn and beyond, Jupiter became a touchstone for every mission that followed. In 1990, the Ulysses spacecraft used Jupiter's gravity to slingshot out of the ecliptic plane, beginning the first mission to study the Sun's poles. In 2000, Cassini, on its way to Saturn, captured high-resolution images that revealed lightning storms flickering through Jupiter's clouds and ultraviolet auroras rippling around its poles. And in 2007, New Horizons, bound for Pluto, passed by for a gravity assist, using the opportunity to image faint rings and volcanic plumes on Io once again. Each encounter, brief but brilliant, refined our understanding of Jupiter's weather, magnetism, and moons. But the true era of intimacy began in 1995, when NASA's Galileo spacecraft became the first to orbit Jupiter. After a 6-year journey, Galileo arrived and released a probe that plunged into the Jovian atmosphere. For 57 minutes, before being crushed and vaporized by the immense pressure, the probe transmitted direct measurements of temperature, pressure, and composition. It found less water than expected, hinting at atmospheric complexity. Perhaps that Jupiter's weather patterns were localized rather than global. The data also confirmed fierce winds exceeding 500 kilometers per hour, immense lightning discharges, and ammonia clouds stacked in multiple layers. The atmosphere of Jupiter was revealed as a colossal heat engine, converting internal energy into never-ending motion. The Galileo orbiter, circling for 8 years, studied the moons in depth. It confirmed Europa's subsurface ocean through magnetic readings and surface flexing, observed Io's hundreds of volcanoes, and detected Ganymede's intrinsic magnetic field, the only moon known to have one. It also captured the ethereal glow of auroras dancing around Jupiter's poles, powered by charged particles funneled by the planet's gigantic magnetosphere. Galileo's mission ended dramatically in 2003, when NASA commanded it to plunge into Jupiter's atmosphere to avoid contaminating Europa, where conditions for life might exist. Even in death, Galileo contributed data. Its instruments recorded measurements until the last seconds, vanishing into heat and pressure 1,000 times greater than Earth's. For 13 years afterward, Jupiter was visited only from afar. But in 2011, NASA launched Juno, a spacecraft unlike any before it, one designed not just to orbit Jupiter, but to see inside it. Whereas Galileo studied the planet and its moons in broad strokes, Juno was built to pierce the clouds, measure gravity, and map the magnetic and microwave environment with exquisite precision. Using a highly elliptical polar orbit, Juno swoops from pole to pole, diving within 4,000 kilometers of the cloud tops before swinging back into deep space to avoid the planet's lethal radiation belts. Each pass, or perijove, provides new data and images that defy expectation. Arriving in 2016, Juno immediately redefined Jupiter. Its cameras revealed cyclones the size of continents spinning around the poles in geometric patterns, pentagons and octagons of perpetual storm. Its instruments detected belts of ammonia extending deep into the atmosphere and gravitational asymmetries, suggesting that Jupiter's core may not be solid, but rather a diffuse region of metallic hydrogen mixed with heavy elements. The planet once thought simple and stratified was instead layered in complexity, its weather reaching thousands of kilometers below the clouds. The Juno mission also gave us our most intimate portraits of Jupiter's auroras. Immense ovals of blue and purple light encircling the poles, generated as charged particles from the solar wind, and Io's volcanic emissions spiral along magnetic field lines. These auroras, thousands of times more energetic than Earth's, are visible even in ultraviolet and X-ray wavelengths, making Jupiter a cosmic lighthouse pulsing across the electromagnetic spectrum. Equally astonishing were Juno's color images. Processed by citizen scientists and researchers alike, they revealed a planet painted in turbulent brushstrokes, bands of copper, gold, cream, and crimson, swirling into whirlpools and ovals like a living Van Gogh canvas. The Great Red Spot, imaged in detail, was found to extend far deeper than anyone suspected, more than 300 kilometers into the planet's atmosphere. And the smaller storms, arrayed across the planet's surface like marbled veins, displayed dynamics that hinted at the role of internal heat rising from the depths. Over time, Juno's findings have transformed our understanding of gas giants. Jupiter is no longer seen as a simple sphere of hydrogen and helium, but as a fluid world with gradients, layers, and storms that stretch beyond imagination. Its weather patterns behave more like fluid dynamics in a star than like any earthly system. The data have even influenced models of exoplanets, the hot Jupiters orbiting distant stars, offering clues to their compositions and formation histories. Looking back, the story of Jupiter's exploration reads like an epic poem of technology and wonder. Each mission added a verse: Pioneer's first courage, Voyager's revelation, Galileo's endurance, Juno's insight. Together, they have transformed our relationship with the giant. What once was a point of light worshipped by ancient astronomers is now a world of energy and storms, its beauty mingled with violence, its magnetism shaping the space around it like a vast invisible shield. And yet, for all that has been seen, Jupiter keeps its secrets. Beneath its swirling clouds, pressures rise so high that hydrogen turns to liquid metal, generating a magnetic field 14 times stronger than Earth's. The planet's interior remains largely unknown, its core a mystery, its heat a paradox. Each orbit Juno completes adds another layer of understanding, another clue to the world that may hold the key to how the solar system itself was born. Because Jupiter is not just a planet, it is the archetype, the firstborn of the Sun, whose gravity shaped the orbits of everything that followed. To understand it is to understand our own beginnings. As Juno continues its dance around the great planet, humanity looks on from across the void, a small species studying a giant, listening to the thunder of creation itself. To gaze upon Jupiter is to see a world of eternal motion. There is no ground, no mountain, no ocean, only atmosphere, stretching down into pressures so immense that the word surface loses meaning. Beneath the planet's painted clouds lies a kingdom of gas transformed by gravity into fluid and fluid into metal. This is not weather as we know it, but a planetary symphony of physics, where light and matter, pressure and heat coexist in forms found nowhere else in the solar system. The story begins at the top, the visible cloud deck that we see through telescopes, the uppermost few hundred kilometers of Jupiter's vast gaseous ocean. Here the colors swirl like liquid marble, cream, gold, and rust red, arranged in alternating belts and zones driven by winds exceeding 600 kilometers per hour. The pale zones are regions where gases rise and cool, forming ammonia ice clouds, while the darker belts are where air descends, clearing to deeper layers. Each band is thousands of kilometers wide and encircles the planet completely, their borders defined by jet streams that blow in opposite directions. Unlike Earth's trade winds, these do not fade with the seasons. They have persisted for centuries, perhaps millennia. Between the belts, vortices form, whirling storms born of turbulence and heat. The most famous of all, the Great Red Spot, has raged for at least 400 years, possibly longer. When Voyager passed by in 1979, It measured the storm at 25,000 kilometers across, large enough to swallow Earth twice over. Juno's modern data show that the red spot extends more than 300 kilometers deep, its roots penetrating into layers where hydrogen itself becomes fluid. Inside that swirling eye, winds reach 430 kilometers per hour, spinning in a counterclockwise rotation in the planet's southern hemisphere. Yet even this titanic storm has begun to change, shrinking slowly over decades, perhaps entering the final chapters of its long existence. If it fades, it will be as though the solar system itself has exhaled. Around it, countless smaller ovals and cyclones churn like pearls in a sea of chaos. Juno's close passes revealed that these storms are organized into geometric patterns near the poles, pentagons and octagons of polar cyclones, each thousands of kilometers across, locked in place by Coriolis forces and temperature gradients. At the North Pole, 8 cyclones spiral around one central vortex, maintaining a perfect symmetry that defies easy explanation. The South Pole holds 6, each slightly larger and bluer in tone. These immense hurricanes do not drift. They remain rooted, eternal features of a world without continents or friction. They are weather carved into geometry. But beneath the storm bands lies something stranger still, the interior of Jupiter, a realm where gases behave like liquids and liquids behave like metals. As we descend through the upper atmosphere, pressures multiply 1,000-fold. Ammonia clouds give way to ammonium hydrosulfide, and finally to water clouds. Yes, water, but at temperatures of several hundred degrees Celsius and under pressures hundreds of times greater than Earth's sea level. Deeper still, hydrogen molecules are squeezed so tightly that their electrons begin to move freely, turning the fluid into an electrically conductive metallic state. It is here, at depths of perhaps 20,000 kilometers, that Jupiter's magnetic field is born, a dynamo of liquid metal hydrogen circulating in endless motion. This metallic hydrogen behaves like nothing on Earth. It is neither solid nor gas, but a shimmering quantum fluid, a sea of protons bathed in a storm of free electrons. If one could descend into it, though no probe could survive, it would glow with an inner silver-blue luminescence, reflecting lightning in metallic gleam. In this strange region, magnetic fields twist and fold, generating a magnetosphere so vast it stretches millions of kilometers into space, reaching beyond Saturn's orbit in the planet's downwind tail. This invisible fortress traps charged particles, creating radiation belts thousands of times stronger than Earth's, a lethal halo surrounding the gas giant. Juno's measurements have upended many of our earlier assumptions about what lies even deeper. Traditionally, scientists believe Jupiter housed a solid core of rock and ice, around 10 to 15 times Earth's mass, surrounded by hydrogen and helium. But Juno's gravity mapping, achieved by tracking minute shifts in the spacecraft's radio signal as it was tugged by the planet, revealed something unexpected. The core is not distinct. Instead of a compact ball of heavy material, Jupiter appears to have a fuzzy core, a vast, diffuse region where metals and hydrogen intermingle gradually. This suggests that Jupiter's interior is not neatly layered like an onion, but stirred and blended, the result of ancient collisions or turbulent mixing during formation. Perhaps long ago, a large protoplanet struck Jupiter as it was forming, dispersing its core material outward and reshaping the giant forever. These findings carry profound implications for planetary science. If Jupiter's heart is diffuse rather than solid, then the traditional model of planet building, in which a rocky seed accumulates gas, may not always apply. Some gas giants may form directly through gravitational collapse, skipping the rocky stage altogether. Juno's discovery has thus blurred the distinction between planets and brown dwarfs, hinting that our solar system's architecture is more dynamic and diverse than once believed. Above this deep interior lies a realm of violent meteorology that dwarfs anything on Earth. Jupiter's lightning flashes through layers of cloud thousands of kilometers thick, illuminating storm columns the size of continents. Unlike terrestrial lightning, which forms in water clouds, Jovian bolts also originate in ammonia water mixtures, creating electrical fields powerful enough to crack molecules apart. Each flash releases energy measured in trillions of joules, a strike that could vaporize a city. Yet even amid this fury, order exists. Juno's microwave radiometer has mapped ammonia upwellings and dry downflows, revealing atmospheric cells that transport heat vertically, much like convection currents in the sun's outer layers. Jupiter's weather is less like Earth's and more like that of a slowly turning star. The energy that drives this colossal engine does not come only from sunlight. Jupiter emits nearly twice as much heat as it receives, radiating internal energy left over from its formation and sustained by gravitational contraction. As the planet slowly cools, it continues to shrink, releasing potential energy as heat, a process known as Kelvin-Helmholtz contraction. This steady outflow fuels the endless storms, ensuring that Jupiter's atmosphere will never truly rest. Its surface, if one could call it that, is a tapestry of moving rivers of hydrogen and helium, boiling from within, sculpted by rotation into long parallel streams. The deeper Juno peered, the more the planet resembled an organism of physics, its belts and zones pulsing with circulation that extends far beneath the clouds. Scientists found that these flows penetrate thousands of kilometers deep, carrying angular momentum through layers of metallic hydrogen. This connection between atmosphere and interior links weather to magnetism, a planetary feedback loop that sustains both the visible storms and the invisible dynamo. Jupiter is, in essence, a self-regulating machine, powered by its own gravity. Even its rain is extraordinary. At certain depths, carbon atoms condense under immense pressure into diamond crystals, falling like glittering hail through layers of liquid hydrogen before dissolving again. Ammonia and water may separate into distinct phases, forming ammonia-rich hailstones that transport energy downward in what scientists call mushball storms. Each process redistributes heat, chemistry, and charge, feeding the circulation that defines the planet's eternal turbulence. Juno's images of these regions, captured in high contrast by its JunoCam, are among the most breathtaking in all of space exploration. They reveal spirals of ochre and cream, iridescent blues at the poles, and storm bands shaped like brushstrokes across a cosmic canvas. Some show white ovals merging, splitting, and reforming, weather systems evolving in real time. Others display filaments of cloud that resemble brushfire smoke, swirling over a boiling sea. Every image is a reminder that Jupiter's surface, though intangible, is alive with perpetual renewal. Beneath those clouds, pressures and temperature continue to climb until all chemistry as we know it ceases to matter. At a depth of 70,000 kilometers, hydrogen and helium become indistinguishable, forming a supercritical fluid that acts as both liquid and gas. The temperature rises to more than 20,000 degrees Celsius, hotter than the surface of the sun. There, Jupiter blurs into its own myth, a planet that is not solid, not empty, but a cosmic storm turned inward, radiating heat like a dying star that never ignited. For NASA, understanding Jupiter is more than curiosity. It is the key to planetary genesis. The gas giant's composition preserves the original chemistry of the solar nebula, hydrogen, and helium untouched since the dawn of time. Within its depth lies the memory of creation, how the sun and planets condensed from dust and gas, how gravity sculpted chaos into order. Every signal Juno sends back, every measurement of ammonia or magnetic flux, is a piece of that ancient puzzle, a record of what the solar system once was before Earth even existed. And so, through the hum of its instruments, Juno listens to Jupiter's heart. Each orbit brings it closer to the truth, that within the clouds and lightning, the hydrogen seas and molten core lies not just a planet but the prototype of all worlds, like it, a cosmic archetype of storms and light. In the silence between data streams, one can almost imagine the thunder rolling through metallic oceans, the roar of heat rising from the abyss. A planet that has been raging for 4 billion years and shows no sign of stopping. Jupiter is more than a planet. It is a system, a gravitational empire whose influence extends across nearly 1 billion kilometers of space. Around its colossal bulk orbit more than 90 known moons, 4 of them large enough to be planets in their own right. Swirling around this central giant, threaded through magnetic fields and radiation belts, they form a microcosm of the solar system itself, a solar system within a planet. From the volcanic heart of Io to the buried oceans of Europa, from the frozen mountains of Ganymede to the ancient plains of Callisto, each moon reveals a different face of planetary evolution. Together, they orbit within a magnetic labyrinth powered by one of nature's most powerful dynamos, Jupiter's own molten heart of metallic hydrogen. The story begins with the magnetosphere, the invisible magnetic field that surrounds Jupiter like a vast, distorted bubble. Generated deep within the planet's metallic hydrogen layer, this field is 14 times stronger than Earth's at the surface, but extends outward into space for millions of kilometers. It is the largest single structure in the solar system. If it were visible to the naked eye, it would appear larger than the full moon in our sky, even from Earth's orbit. Its sunward edge, called the magnetopause, faces the solar wind like a shield, while its tail, the magnetotail, stretches past the orbit of Saturn. Within this immense domain, charged particles spiral along field lines, creating belts of radiation so intense they can fry spacecraft electronics in minutes. Jupiter's magnetosphere is not static. It is alive, constantly breathing and shifting in response to the solar wind. The planet's rapid rotation, once every 9 hours and 56 minutes, drags its magnetic field around like a turbine. As it spins, plasma from the volcanic moon Io becomes trapped in the magnetic lines of force, forming a glowing plasma torus that circles Jupiter's equator. Io, eternally tortured by Jupiter's gravity, erupts with hundreds of sulfur volcanoes spewing a ton of gas every second into space. These particles become ionized and accelerate along the magnetic field, creating an electric current that flows between Io and Jupiter, a giant electromagnetic circuit generating up to 5 trillion watts. The current produces radio emissions so powerful they can be detected from Earth, turning Jupiter into a natural radio beacon pulsing across the cosmos. Where these charged particles collide with the planet's atmosphere, they produce auroras, rings of light at the poles that outshine all others in the solar system. Unlike Earth's auroras, which shimmer in transient bursts, Jupiter's are permanent. The main auroral oval glows continuously in ultraviolet, while secondary spots mark where its moons connect magnetically to the planet. Io, Europa, and Ganymede each leave a visible footprint of light upon Jupiter's polar regions. These glowing footprints are not mere curiosities. They are signatures of electrical coupling, evidence that Jupiter and its moons are linked by invisible power lines stretching through the plasma-filled space between them. The entire system hums with electromagnetic life, a cosmic orchestra of current and field. Among the moons, each plays its role in this magnetized drama. Closest to Jupiter, Io endures the most extreme conditions. The planet's gravitational pull flexes its interior by hundreds of meters every orbit, generating intense tidal heating. This friction melts rock into magma, making Io the most volcanically active world in the solar system. Its eruptions blast sulfur and oxygen high into space, feeding Jupiter's plasma torus. The constant stripping and replenishment of material make Io's orbit a perpetual engine, its volcanic heartbeats in rhythm with Jupiter's magnetic pulse. Beyond Io orbits Europa, a smaller, colder world cloaked in an icy shell. Beneath that shell lies something extraordinary, a global ocean of liquid water, kept warm by the same tidal flexing that torments Io. Galileo's magnetometer first detected magnetic fluctuations around Europa, implying an induced magnetic field, a signature of conductive saltwater beneath the crust. Later observations confirmed it. Today, Europa is one of the most promising places in the solar system to search for life. Jupiter's magnetic field, sweeping past at 74 kilometers per second, induces electrical currents in the ocean below, stirring its depths like a planetary dynamo. Every time the field reverses, the ocean responds, whispering its presence through subtle electromagnetic echoes that Juno continues to record. Farther out lies Ganymede, the largest moon in the solar system, even bigger than Mercury, and a world of geological surprises. Beneath its cratered crust lies another ocean, possibly 100 kilometers deep. But Ganymede stands apart for another reason. It possesses its own intrinsic magnetic field, the only moon known to have one. This field interacts with Jupiter's, creating a magnetosphere within a magnetosphere, a nested bubble of magnetic complexity. Auroral ribbons ripple across Ganymede's poles, driven not by sunlight, but by the magnetic handshake between moon and planet. Then comes Callisto, ancient and far-flung, its surface a frozen record of 4 billion years of impacts. It, too, may hide a subsurface ocean, faintly conductive, though it lies beyond the reach of Jupiter's strongest tides. Together, the 4 Galilean moons form a hierarchy of heat and distance. Io, the volcanic inferno; Europa, the ocean world; Ganymede, the magnetized giant; and Callisto, the silent relic. Their diversity is a direct result of Jupiter's influence, its gravity, magnetism, and radiation sculpting each according to its orbit. Jupiter's magnetic field does more than shape its moons, it sculpts space itself. As charged particles stream from the sun, they are deflected and captured, creating a magnetotail that interacts with the solar wind like a living membrane. Instruments aboard Juno have measured magnetic reconnection events, explosive releases of energy. Wind field lines snap and rejoin, hurling plasma outward. These phenomena mirror those seen on the Sun and Earth, showing that Jupiter is not merely a passive giant, but an active participant in the solar weather system. The complexity of this environment forced engineers to design spacecraft like armored vaults. Juno's electronics are housed within a titanium vault to shield them from radiation 20 million times stronger than Earth's. Even so, each orbit exacts a toll. Instruments degrade, data transmissions weaken, and yet Juno continues to endure, its polar trajectory allowing it to dive beneath the most dangerous zones while gathering data from above the poles, where the magnetic field lines converge in luminous storms. Through Juno's eyes, the auroras of Jupiter have become one of the great spectacles of science. In ultraviolet and X-ray imagery, they pulse and flare like cosmic heartbeats. Bursts of megavolt electrons spiral into the atmosphere, colliding with hydrogen molecules and releasing light across multiple wavelengths. Unlike the fleeting curtains of the northern lights on Earth, Jupiter's auroras blaze continuously, their energy driven both by the solar wind and by the motion of the moons. When Io's volcanoes intensify, the auroras brighten. When plasma density changes in the magnetosphere, their shape shifts. The planet's magnetic poles become literal gateways of energy, converting motion and magnetism into radiant fire. The interplay between Jupiter and its moons is more than spectacular. It is a model for planetary systems across the galaxy. What happens around Jupiter happens around other gas giants, and perhaps around distant exoplanets with their own moons. The electromagnetic coupling, tidal heating, and subsurface oceans we see here may be universal, offering countless niches for habitability. In studying Jupiter's magnetosphere, NASA is also studying the physics of stars and exoplanets, the rules of magnetic weather that shape entire worlds. Jupiter's system also serves as a time capsule. The composition of its moons preserves the chemistry of the early solar system. Ganymede's water, Europa's salts, Io's sulfur, each bears the fingerprints of primordial materials mixed by Jupiter's gravity. The giant's magnetosphere acts as both destroyer and preserver. Radiation sculpts surfaces, erasing old ice and creating new chemistry, while shielding the inner moons from the full force of solar wind. Within this balance of chaos and protection, new compounds form, perhaps even the precursors to biology. From this perspective, Jupiter becomes less a planet and more a cosmic engine, turning gravitational energy into heat, magnetic energy into light. It binds its moons in a synchronized dance, each locked to the others in orbital resonance, their motions creating rhythmic tides and internal heat. The resonance of Io, Europa, and Ganymede, 1, 2, 2, or 4, ensures that their orbits never settle, keeping their interiors alive. The system sustains itself, a perpetual motion of matter and magnetism that has endured for 4 billion years. As Juno continues to orbit, its sensors record the whispers of this machine, the oscillations of plasma waves, the flicker of auroral currents, the silent pull of magnetic field lines extending into the void. Every bit of data enriches our understanding of how planets shape their space environment. When future missions, such as Europa Clipper and JUICE, Jupiter Icy Moons Explorer, arrive, they will explore this system with a new awareness, not as isolated moons but as components of a vast interconnected world bound by magnetism and motion. Jupiter teaches us that a planet's influence does not end at its surface or even in its atmosphere. It extends into space itself, sculpting invisible architectures of energy. The gas giant's magnetic field, born from the depths of metallic hydrogen, reaches outward like a solar wind of its own, touching the icy skins of distant moons, stirring oceans beneath their crusts, and painting light across the void. In the end, what NASA found on Jupiter is not only a planet, but a principle, that nature repeats itself in fractal form. The great and the small reflect one another. Jupiter mirrors the sun, its moons mirror the planets, and within that mirror lies the blueprint of creation itself. The giant storms, its auroras, its living magnetosphere, all are echoes of the same forces that shape galaxies. And so, Jupiter turns endlessly. Its clouds roll, its lightning flashes, its magnetic heart beats beneath the veil of hydrogen. Around it, its moons orbit like faithful worlds in miniature, their own seas and volcanoes illuminated by the reflected light of a storm that never ends. In the stillness of space, the entire Jovian system glows like a clockwork of light, a solar system within a planet, alive, eternal, and profoundly beautiful.